Hello everyone and welcome to my channel. My name is Dr. Korachi, and in this video lecture we will cover security architecture. Now, let me give you a real world example. The 2021 SolarWinds sunburst supply chain attack exploited weak network architecture and insecure application integration across thousands of organizations. Now, the attackers basically moved literally for months because segmentation, zero trust, and secure development practices were missing. Therefore, the lecture emphasized security by design rather than bloating controls on after deployment. Now, before we dive into the 5 objectives, you're looking at it on the screen over here. Let's first review the agenda to understand the structure and the flow of this lecture. That way, each section will build on the previous one here. So, what we will cover? We will discuss network architecture. We're going to talk about infrastructure design. We're going to talk about secure application integration, data security, and finally, authentication and authorization. So, in the section 1 here, we're going to talk about secure network architecture. Now, this section requires analyzing security requirements and integration and basically integrate them into an appropriate network design. Now, specifically, it encompasses services, like IDS, IPS, WAF, segmentation strategy from VLANs to microsegmentation, zero trust principles, network merging challenges, and software-defined networking. The key takeaway is that network architecture is no longer set it up and forget about it. It must continuously adapt to cloud workloads, remote work patterns, and zero trust models. As a result, static perimeter-based security is insufficient for modern enterprises. Now, why is security network architecture important? The 2017 Equifax breach succeeded largely because of the flat network design and unsegmented internal systems. Had proper microsegmentation been in place, the blast radius of the Apache Struts vulnerability would have been contained to the initial compromised server rather than spreading to databases containing 147 million records. Now, let us begin with the first major topic in the network architecture, IDS and IPS detection methods and deployment types here. So we will start first with the signature recognition. Now, the signature-based detection here matches known attack patterns from preloaded databases, making it fast and precise for known threats. However, it is fundamentally blind to novel or encrypted attacks because it can only match what has already been cataloged. Now, for example, if you're familiar with the Snort, which is the most widely deployed open source IDS, Snort supports 7 custom rules you're looking at right here. The alert, the log, pass, activate, drop, reject, and stop. Now, for instance, within hours of the 2017 WannaCry ransomware outbreak, Snort signatures for the external blue exploit were widely distributed, enabling signature-based detection across thousands of networks. However, the initial wave of infection occurred precisely because no signature existed for the 0-day at the time of the release. Now, the second one is the anomaly-based detection. It builds on the baseline of a normal network behavior over days or weeks. then flags any deviations from that baseline. Now, as a result, it excels at detecting zero-day attacks that no signature can match. However, the trade-off is a significantly higher false positive rate, which contributes directly to alert fatigue. For instance, during the 2020 SolarWinds Sunburst attack, anomaly-based tools at several organizations detected unusual beaconing patterns to external C2 servers that no signature database could have matched because the malware was custom built. Now, in the third one, the protocol decoding resembles packets and models the full TCP stack specification to expose higher layer activity that simple packet inspection would miss. As a result, it can detect sophisticated evasion techniques, such as custom TCP stack manipulation. Like you could use tools like Nmap or HPing3 where you manipulate TCP stack, for example. Now, however, this method requires the IDS to maintain full session state and understand application layer protocols, which increases computational overhead. Finally, we have the alert fatigue. Now, alert fatigue occurs when the sheer volume of alerts overwhelms the SOC analyst, Security Operations Center, making it impossible to distinguish true positives from false positives. To mitigate this, organization deploy tiered SOC responder like L1, L2, L3, and implement thresholds tuning using the three approaches, the one you're looking at it here on the screen. The first is called fixed threshold, state-based threshold that adapt to system conditions, historical threshold that leverage the trend data. However, NIST now, by the way, using the IDS and IPS, they combine them together as a standard naming. They call them IDPS, by the way. Now that we understand how IDS and IPS detect threats, the next question is, where do we place them? Let us examine the different types and their optimal deployment position in the network in the next slide. Now, when looking at the table, you will notice there is IDS, IPS type comparison table right here. This table provides a systematic comparison of 6 different types you're seeing right here on the screen. Now, so let's take a look at each one of them. The first one is the network IDS. It monitors network packet passively at the perimeter. However, it cannot inspect encrypted traffic, which is a critical limitation given that over 90% of the web traffic now uses TLS. So, as a result, it's the best for placing it at the perimeter DMZ monitoring. Now, the second one is the host IDS, which basically operate at the host level, and it can inspect traffic after TLS decryption occurs. You see, look at that right here. Now, although it is passive and cannot block attacks, it excels at the file integrity monitoring and process auditing. Now, by the way, for instance, during the 2013 Target breach, an internal IDS flagged unusual activity on the POS servers, point of sale, after the initial NIDS missed the compromise. Now, third, network IPS sits in line, on the network and actively blocking threats. Now, despite this advantage, it shares the network IDS inability to inspect encrypted traffic here. The fourth one, here we have the host IPS. It combines host level visibility with active blocking capability, making it the most comprehensive single host solution. It inspects after decryption and can block malicious process in real time. Fifth, we talk about wireless IDS and wireless IPS here. Okay, now both they address wireless specific threats. Now, let's examine different placement strategies here, starting with the DMZ screen subnet. Now, the sensors here detect perimeter attacks, but miss attackers who have already gained internal access. Internal network sensors, detect lateral movement. They should be placed on the mission critical systems. Inline dual sensor, architecture deploys a signature-based sensor first, followed by a heuristic sensor second, which prevents any single IDS from becoming a performance bottleneck. With detection and placement understood, let us now examine the network services that IDS, IPS must protect, starting with those you're looking at the screen. Now, let's understand the different network services being implemented in enterprise, starting with the WAF, which stands for Web Application Firewall. This thing operates at the layer 7 of the OSI model. It protects web application against OWASP top 10 attacks, including XSS, SQL injection, cookie poisoning, and some others. However, it is critical to understand that WAF is not a replacement for traditional network firewall. It complements one. Okay. Now, for the NOC, which stands for Network Access Control, it verifies device health and compliance before granting network access. There are 4 deployment types here. Now, you have the infrastructure-based, which requires hardware upgrades. You got the endpoint-based, which basically are software agents installed on the devices. And you got the hardware-based agentless AD, which is leveraging Active Directory. Now, as a result, the NAC enforces the verify before trust principle that underpins zero trust here. Now, the VPN is a method, not a protocol. It uses IPsec, which operates at layer 3, while SSL, TLS, VPNs operate at the layer 7 here. There are 2 types, hardware and software. The hardware VPN offload encryption from the CPU, while software VPN are easier to deploy. There are 3 standard placements, can be done here. Could be like parallel to the firewall, within the screened subnet, or integrated into the firewall appliances. Next, we have the load balancer here. Now, the load balancer distributes the traffic at the layer 4, the transport one, or layer 7, the application. Beyond performance, they enable rolling upgrades and provide centralized defense point for DDoS attacks here. Now, the forward reverse proxy intercept client to internet traffic for monitoring and filtering. Reverse proxies sit at the network edge, scrubbing inbound traffic, providing DDoS protection and load balancing. Finally, we have the DNSSEC, which is security. It's digitally signs DNS response to authenticate the server. However, it does not provide confidentiality, does not protect against DDoS, and does not prevent domain hijacking. Now, what we discussed closely mirrors, by the way, the 2019 Capital One breach, in which a misconfigured WAF, okay, and an overly permissive IAM role enabled a former AWS employee to extract 100 plus million customer records. Now, these services you're looking at protect individual network traffic, but how do we architect the network itself to limit an attacker's ability to move between segments? Let's bring us, that brings us to the network segmentation strategy over here. Now, in this slide, we look at different network strategies. We gotta look at the VLAN, microsegmentation, jump box, screen, subnet, DMZ, data zones, air gap, VPC, VNet, availability zone. Let's look first at the VLAN. Now, the VLAN segment traffic at the switch level, reducing broadcast domains and providing logical separation without physical network changes. However, they are vulnerable to VLAN hopping attacks via the dynamic trunking protocol. Now, as a result, the critical mitigation is to disable DTP, dynamic trunking protocol, on all user access ports. The second one, we have the microsegmentation, which divides the data center into granular security segments with the application level policies. Now, as a result, it is the most effective architectural defense against lateral movement. Now, jump box is a hardened device used exclusively for administrative tasks across security zone. It must never be used for email, web browsing, or any non-administrative function. Now, by the way, the industry is evolving the jump box into a secure admin workstation with even stricter hardening. Number 4, the screen subnet sits between the internet and the internal network, hosting public-facing services like a triple-homed firewall. Now, this architecture ensures that a compromise of a public server does not directly expose the internal network here. Now, number 5, data zones have 3 types, okay? Now, the first one is basically the vector-oriented, which means disable USB and auto-run to prevent physical attack vectors. The number 2 is the information-centric, layer controls directly on the data. And the last one is the protected enclaves, combine VPN and the firewalls to create isolated trust zones. Now, the air-gapped networks have no network connectivity. Despite this, they remain vulnerable to insider threats, and the physical attacks, Now, the most famous one, by the way, is the Stuxnet back in 2010, which bridged the air gaps at the Iranian nuclear facility via infected USB drives. The 7th, we talk about the virtual private clouds. It provides on-demand secure environments within public cloud providers. Virtual private clouds are software defined with the full IP, subnet, and routing controls. Now, Both enable microsegmentation in a cloud environment. Now, finally, availability zone, that's where you have like multiple physical data centers within a single geographical region, provide failover and redundancy. For example, Amazon Web Services availability zones feature kept Netflix at that time running during 2017. When that happened, they called AWS US East -1 outage because traffic automatically shifted to a healthy zone. Now, to understand the importance of network segmentation strategy, consider the 2017 Equifax breach, which resulted, from a flat network architecture that allowed attackers to move from the compromised Apache Struts server to database containing 147 million records. Now you understand the segmentation role. Let's examine the zero trust principles and the deparameterization drivers that make them necessary in the next slide over here. Now here we have the zero trust, here we have the deparameterization drivers. Now the zero trust, it's a very important concept. It basically replaces the old trust but verify model with never trust, always verify. Now there are four core principles. The first one, never trust by default. Every access request is authenticated, regardless of the network location. Number two, we have the strong identity verification. That's a single source of truth for user identity, with mandatory MFA, for both user and the machine. Third, strict access policies, least privilege enforce peer application rather than peer network. And fourth, cloud awareness, security boundaries must be extended to cloud, remote work, mobile, outsource, and wireless environment. Now, let's understand the deparameterization driver here, starting with the cloud computing. Now, cloud computing places assets outside organization boundaries, as you know, requiring trust verification with the cloud provider controls. For remote work, accelerates dynamically by COVID-19, introduced millions of users who frequently circumvent VPN policies. The mobile devices, expand the network boundary beyond physical walls, necessitating, by the way, the use of mobile device management in companies and remote wipe capabilities. Outsourcing here, grants third-party access to internal network, demanding service level agreement, of course, operational level agreement, and periodic security audits here. Now, finally, here we have the wireless and RF technologies, like Wi-Fi 6 saturated, by the way, enterprise. We all use Wi-Fi 6, Wi-Fi 6E. Now, in enterprise, it's highly recommended to use WPA3, to replace the vulnerable WPA2 so far. Now, as a real-world example, the 2022 White House Office of Management and the Budget Zero Trust Strategy mandate those principles I just mentioned in this slide across all federal agencies in a direct response to the SolarWinds breach, which demonstrate how traditional perimeter security failed miserably against a sophisticated supply chain attack. So, we understand that zero trust is an architecture philosophy. Now, let us shift to the infrastructure security design, which examines how to design the infrastructure itself to be scalable, resilient, and automated. Now, this section focuses on designing infrastructure that survives failures and scales, elastically. Specifically, it covers vertical and horizontal scaling, high availability and redundancy patterns, by looking at, scalability, resilience, automation, containerization, virtualization, CDN, and so on. Now, the core design principle is that resilient infrastructure is not an afterthought. It must be architectured from the ground up with failure modes explicitly planned for. For example, back in 2021, Fastly CDN outage took down major websites worldwide, including Amazon, Reddit, and UK government portal, demonstrating why proper CDN configuration and failover mechanisms are critical. Let us begin with the foundational infrastructure concepts, scalability, resiliency, and automation over here. Now, let's understand first of all, what scalability and models. The first one here we have the vertical scaling. Basically, it adds resources like CPU, RAM, or storage to an existing machine. Although simple, it has a hard ceiling defined by the hardware's maximum capacity. Furthermore, it creates a single point of failure. The horizontal scale out, adds additional machines to distribute the workload. Now, this approach enables cloud elasticity and is the preferred model for high availability architectures. As a result, most common cloud native applications are designed for horizontal scaling from the start. Auto scaling dynamically adjusts the cloud resources based on the demand, improving both fault tolerance and cost management. As a result, organizations pay only for the capacity they actually use. Now, in the next here, I want to make sure that you understand resilience and automation. Now, when we look at high availability, and there's redundancy, replication, clustering, SOAR, and bootstrapping, CI/CD. Let's first look at the high availability. High availability is measured as a percentage of uptime, 99.9%. They call it the three nines. Allows approximately 8.76 hours of downtime per year, while the last one, the 5 nines, allows only 5.26 minutes. The level required depending, of course, on the SLA and the business requirements. Now, for redundancy, deploys multiple assets in the same role as that can replace another on failure. Replication ensures data is shared across hardware and software mechanisms to maintain stability and consistency. Clustering group of systems so that if one fails, the remaining nodes absorb its workload seamlessly. Now, this is the foundation of enterprise database and application server deployment. Now, the SOAR, which stands for Security Orchestration, Automation, and Response, what does it do? It automates incident response workflow, reducing mean time to respond and freeing analysts for higher order tasks. The final one, the bootstrapping, is the VM initialization sequence that configures a new instance from a baseline image. And finally, the CI/CD, okay, which stands for continuous integration, continuous delivery. It automates the build, test, and deployment pipeline, reducing overall project cost and human error. Now, with the infrastructure design, okay, covered, let's move on to section 3, how to integrate applications securely using SDLC, DevSecOps, and application security testing. Now, let's take a look at the section 3. The purpose of section 3, or it covers basically secure application integration, including baseline, SDLC, DevSecOps, CI/CD, and different practices, including OWASP Top 10. The core principle is shift left. Security must be built into the development process from the earliest stages rather than tested in at the end. Okay, so let us start with the 3 primary application testing methods. Okay, let's start with the first one, static application security testing here. So you can understand the difference between those 3. Now, in static application security testing, it analyzes source code without executing it, making it ideal for early detection during development. The shift left principle, that's it. However, it cannot detect runtime vulnerabilities, such as authentication flaws or race conditions, The second one, the dynamic application security testing here, it tests the running application from the outside using a black box approach. No source code access required. As a result, it catches issues that only manifest during execution, like authentication bypass or XSS, For example, by the way, OWASP ZAP, which is, if you're not familiar with it, the most popular open source DAST tool. Okay, it discovered runtime XSS vulnerability during penetration tests that the SAST could not find it or discover it. The last one is the interactive application security testing. Combines both you're looking at here by deploying an agent inside the application that monitors code execution in real time. As a result, it provides the most comprehensive coverage by simultaneously accessing code configuration, runtime behavior, and library dependencies. Now, per Grotner, the IAST is now required for modern web and mobile application. Now, the fuzzing, they're using it to inject large volumes of unexpected or malformed input to trigger crashes and expose weaknesses. It works alongside any testing approach. Tools include American Fuzzy, LLP, and some other different type of custom fuzzers here. Now, finally, let's review the common criteria, the evaluation assurance level. By looking at the screen, you see that there are 7 levels over here. Okay. They serve as the international gold standard for verifying that IT products meet defined security claims. At its core, the framework uses equivalent assurance levels, okay, from 1 to 7, there, it's there's 1, 2, 3, 4, and so on, that reflects the depth of the evaluation process. Now, number one, okay, basically indicate that the product is merely functional tested here, okay, to confirm that it works as advertised. Now, if you look at, number 7 is formally verified. That basically considered the most secure and rigorous mathematical proof of its security architecture. Just to be aware of, for the majority of the tech industry, the number 4 eval, or the evaluation assurance level 4, stands as the highest level that is both commercially valuable and globally recognized, representing a product that has been, tested under this category, provides a meaningful level of confidence for enterprise grade hardware and software without the higher cost associated if you start going down here. Now, let's look at the NIST 800-64, the 5 SDLC phases. Now, in the phase 1 here, this is the initiation requirements, establishes the system need through feasibility studies and identify security requirements from the outset. This is where the threat modeling should begin. Now, in phase 2, deployment, acquisition encompasses design, programming, and procurement. Security requirements are finalized and acquisitions are completed during this phase. Now, in phase 3, deployment or fielding involves validation, acceptance of testing, and release. All security controls must be verified before the system enters production. Now, phase 4, operation maintenance, is where the system performs its stated work. This phase includes patching, configuration, changes, upgrades, and continuous monitoring. In fact, this is typically the longest phase and where most security incidents occur. Now, in the last phase, disposal and reuse, decommissioning, that's what it means. Data remnants must be managed through 7 pass wipes or by physically destroying storage media, like crushing, drilling, shredding. Now, let's take a look at the different deployment approaches, starting with the SecDevOps. Okay. This one here integrates the security directly into development operation workflow from day one. Developers consider security standard as part of their daily work. Agile uses iterative component-based, okay, and it's basically prioritizing working software. The waterfall is sequential and simple, but poorly suited for complex projects. Spiral, okay, it's a risk-driven with the client review at each phase. Best for large projects, but slower and more expensive. Now, the last one is the CI/CD pipelines. It automates integration, testing, and deployment, reducing both cost and human error. Now, let's examine the next slide, the OWASP Top 10. Now, the OWASP Top 10 application security risks here. Obviously, each one of them requires in-depth reading and practicing and, learning each one of them. But we're going to cover just the basic things. Starting first with the broken access control, which basically it's a failures allowing unauthorized access to resources. The second one is the cryptographic failure. They used to call it sensitive data exposure. It covers weak or absent encryption of sensitive data in transit and at rest. Number 3, the injection attacks, including OS commands injection, SQL, LDAP, and expression language injection, in which attacker controlled data alters intended queries or commands here. Now, insecure design, okay, emphasizing that security flaws baked into the design phase cannot be fixed by perfect implementation here. Number 5, security misconfiguration covers default credentials, open cloud storage buckets, unnecessary features enabled, and missing security headers here. A6, vulnerable components here and outdated components. These addresses the supply chain risk of running libraries, frameworks, or OS components with known vulnerabilities. Number 7, we have the authentication failure. They call it identification and authentication failures, which covers broken authentication mechanism, including weak password, session fixation, and MFA bypass. 8, security integrity failure and data integrity failures. They target the CI/CD pipeline compromises, okay, unsigned software updates, and insecure deserialization. Now, number 9, logging failure. They call it the security logging and monitoring failure. It highlights the insufficient logging, Finally, we have the A10 SSRF, okay, which stands for server-side request forgery, where the server is tricked into fetching the attacker's supplied URL, bypassing firewalls and access controls. Now, with the application security covered, let's move to section 4. That's where we start discussing the data security techniques, where we examine how to classify, protect, and manage data throughout its life cycle. Now, the data security techniques section opens with a focus on these technologies you're looking at right here. The fundamental principle is that data must be classified before it can be protected effectively. Classification drives every subsequent control decision, by the way. Now, let's take a look at the data classification, the DLP obfuscation, starting with the government data classification. You look at it here, there's the top secret. That's like a great damage to national security, secret, serious damage, like to national security. Confidential could cause damage. Unclassified, non-sensitive. Okay. Now, for commercial, confidential, most sensitive, internal only. Sensitive, less causes damage. Private, personal, like medical, HR, public, no damage from disclosure. Now, let's review key concepts, starting with what's called the obfuscation. Okay, the techniques. The 4 key techniques protect data while maintaining utility are. The first one is the tokenization. The tokenization replaces sensitive data with the unique non-sensitive tokens. No exploitable value remains. For instance, the PCI compliant payment processes use tokenization, so the actual credit card number never touches the merchant's application. Now, the second one, scrubbing. The scrubbing, also they call it cleansing, fixes or removes duplicate or incorrect data from data sets. Masking hides or filters data so only approved fields are visible. The classic example being is the credit card masking. You see it right here. Okay. Now, finally, anonymization remove all identity attributes, from data, so it remains useful for analysis, but cannot be attributed to any individual. Now, classification and obfuscation protects data at the content level. Now, let's examine the full data lifecycle and the RAID-based storage security. Now, the data lifecycle, you look at it here, it has 6 phases: create, use, share, store, archive, and destroy. Now, security control must be applied at every phase, not just during storage. The destroy phase is particularly critical. Any data remnants requires, like I said before, 7-pass wipes or physical destruction of storage media to prevent recovery. Now let's take a look at the RAIDs. Okay, now we have RAID 0, RAID 1, and others here. Let's take a look at the RAID 0. Now, the RAID 0 is a stripping, which provides maximum speed, but 0 fault tolerance here. One drive fails, forget it, you lose all your data. RAID 1, mirroring, creates an identical copies of data across the 2 drives. So, you should have 2 drives. RAID 5, stripping with priority, distribute priority data across 3 or more drives, balancing speed and redundancy. And finally, RAID 10, mirrored stripes, requires a minimum of 4 drives and delivers both fault tolerance and performance, which is the enterprise standard. Now, before I move on, I want you to understand that RAID is not a backup solution. It provides only fault tolerance for drive failures, but does not protect against ransomware, accidental deletion, or data corruption. Why? If you delete, for example, like in RAID 1 mirroring, if you delete one data, that deletion will go into the mirrored drive here. Now, the storage security controls have 5 foundational controls to protect the storage system. Like, starting with the asset inventory, which means know what you have, security policy, define how is it protected. Now, of course, we spoke about IDS, IPS plus firewall. System hardening, reduce attack surface by removing unnecessary services or application. And finally, patch management, maintain currency and security updates. Now, data security is only effective when the right people have the right access. That brings us to our final objectives. Section 5, authentication and authorization controls. The final section called authentication and authorization. It covers several topics. We're going to discuss it next slides here. Let's examine first one is the access control models here, starting with the mandatory access control. Now, by the way, the mandatory access control is used primarily in the government environments where the system enforces security level like top secret, secret, confidential, and so on. Overriding MAC requires senior management authorization. Basically, it provides the highest level of access restriction, but it is also the least flexible. Now, discretionary access control allows the resource owner to decide who gets access. Using like access control list, like read, write, and Unix style permission. It is the most common model in commercial operating system like Windows servers, for example, or Linux or Unix. However, it is also the most vulnerable to insider threats because owners may grant exclusive permissions. Third, role-based access control assigns permission based on organizational roles rather than individual identities. The process follows a clear chain. Role assignment lead to authorization, which leads to permission. Now, this model significantly simplifies administration in large organizations. Now, rule-based access control applies ACL rules to objects. For example, like firewall rule sets are the classic example. Rules are processed top-down with an implicit deny all at the end. Finally, we have the attribute-based access control is the most granular model, evaluating access based on user attributes, resources attributes, environmental conditions, and their relationships. It is best suited for complex enterprise environment where simpler models cannot express the required policy. Now, next here, you're looking at the authentication protocol. There are plenty different types of application protocol. Let's start with the radius. Encrypts only the password and is used with EAP and 802.1x for remote access. Okay, the AAA. Now, the TAC ACS Plus, this is a Cisco AAA. It encrypts full packet and separate basically the authentication, authorization, and accounting into distinct, into like a separate processes here. Now, Kerberos, which is use a ticket-based flow, like KDC to ticket granting ticket to the ticket services. And has been the default in Windows servers since 2000. And here we have the LDAP, directory access. There are LDAP and LDAP-S. The LDAP uses port 389 and the LDAP-S port 636 provide directory access. And here we have also the authorization. This provide access tokens, no credential exposure here. And 802.1x, this one is a port network access control. It uses this protocol. It focuses on the user to authenticator to authentication server. And the last one is SAML, which is the cross-domain SSO. It's use XML based organization to organization authentication and authorization. Now let's examine the specific authentication factor like OTP, mechanism, SSO risk, and hardware roots of trust over here. Now let's review the multi-factor authentication over here, type 1, 2, 3, and 4. Let's start with type 1, something you know, like password, passphrases, that something you know. Type 2, something you have, like badge, token. Type 3, something you are, like biometrics basically, like fingerprints, retina scan, voice prints. And type 4, somewhere you are, like GPS, IP restrictions, and geolocation. Now, remember something, that the two-factor authentication must use two different factors. Using two passwords, like type 1 plus type 1, does not qualify. Next, let's look at the OTP methods, the one-time password. Now, there are several things, starting with HOTP, which is stand for HMAC-based one-time password. It's a counter-based. The code remains valid until a new one is requested. YubiKey is the most common HOTP hardware device. Now, the TOTP time-based OTP uses a clock-based timestamp of 30 to 60 seconds and expires automatically. Authenticator application, like Microsoft Authenticator, I'm sure you're using it, or Google Authenticator uses this technology. Now, for channel types, we have the in-band same channel authentication. It sends the code via the same channel, like SMS to the same phone, making it vulnerable to SIM swapping and interception. Out-of-band authentication sends the code to a separate device or channel, which is required in healthcare and banking environment. Now, the SSO Kerberos enables single sign-on to all authorized resources. However, it creates a single point of failure, a one compromise of one credential. The attacker gains broad access. Now, obviously, a mutual authentication is required to prevent man-in-the-middle attacks. Finally, we have the TPM, hardware root of trust. Now, it's a crypto processor chip on the motherboard that provides hardware-based key storage, major boot, and attestation over here. Now, by the way, Google in 2021 auto-enrollment of all users into two-step verification using TOTP and YubiKey HOTP devices prevent the vast majority of credential stuffing attacks against Google accounts. Now, let's summarize what we have covered in this video lecture. We talked about defense in depth, meaning layering controls from network edge to endpoint, no single control, whether IDS or WAF or VPN or access control is sufficient on its own. They must work together as a coordinated system. The second one is the zero trust architecture, which represents a fundamental shift from perimeter-based security. The three pillars are strong identity verification, mandatory MFA, and the least privilege are its three pillars. Security by design, we spoke about different type of techniques and methods of securing development. Classify before protecting. Now, reinforce that data classification must precede all protective controls. Now, classification, drives DLP policy, encryption requirements, access control decision, and storage security configuration. Number 5, authentication and authorization confirms who you are. That's the authentication. Authorization, it determines what you can access. And finally, resilience requires planning. This reminds us that RAID is not a backup. It's high availability. So high availability is not a disaster recovery as a complete solution. And scaling must be planned for both vertically and horizontally. All rollback procedure must be documented in a change management system, which is a complete different topic over here. And finally, I want to thank you for watching this video. If you like it, please hit the like button and subscribe to my channel for more videos. Thank you so much for listening.